Good morning, everyone. You'll be starting class in 1 to 2 minutes' time. Alright, good morning, everyone. And in today's session, we're going to be focusing on the content in the Matlab 1A exercise that was posted on my learning. Now, if you did not start the Matlab on-ramp certification course, I highly suggest that you do get a start on it, because some of the material that will be coming here today relies on some prior knowledge inside that particular course. So hopefully you already started it, either you're in progress or you completed it, and you already have been exposed to some of these core concepts that we're going to be discussing today. So the first thing, one thing before I start, if you have any questions during this lecture, feel free to interrupt me in the chat. Once I'm finished talking about the point that I'm on, I'll answer them accordingly in order as they come inside the chat itself. So the first thing that we're going to be starting on today is the use of notations and subscripts. So we know that basically Matlab is basically a scripting language. It's not a programming language, such that the difference between the two is that you need the Matlab engine, or this entire Matlab GUI here, to run any of its code or script, which is commonly referred to. And without this Matlab engine here, this entire Matlab program, you cannot run any of the script. Whereas compared to code or actual coding languages, which is different from scripting languages, you actually can build a program using that coding language. And then you don't need that compiler again anymore to run that program. That program can actually execute by itself. So that's going to be the key difference between scripting and programming languages as you go about during your courses this particular semester. So short version, MATLAB scripts, you actually need the entire MATLAB program to run it. Coding languages, once you build your program, you don't need the compiler anymore. That program will run without the compiler, and it can run on almost any system that you built it for entirely. So MATLAB, basically, we're going to be storing a lot of our variables or any data constructs and named variables that we're going to be using here in the command window. So if we wanted to make a one-dimensional vector here, let's say a is equal to 1, 0, 0, 1, we basically make a full row vector here with these 4 values which are separated by spaces. If we did not want for this output here to be given when we typed it, we can just hit up on our keyboard here, and we can get our command history. And instead of having this command just being by itself, we could put a semicolon. And this semicolon just suppresses the command output that we saw here previously. If we wish to make this same row vector here into a column vector, let's call this AC. That means now we'll have to put 1, semicolon, 0, semicolon, 0, semicolon, 1. And if we type in AC here, we see that now it is an actual column vector instead. So these semicolons here inside the brackets separate the new rows within your vector, or when we go a little bit more complex, within your matrix. And then similarly, if we wanted to make, let's say, a 3-dimensional matrix, we can say common A here is equal to 1, 0, 0, semicolon, 0, 1, 0, semicolon, and then 0, 0, 1. And then if we just hit common A here, we see we get our 3-dimensional matrix as required. So in using the construct here for your vectors and matrices, spaces means that you're on the same row. A semicolon means that you're going to be starting on a new row within either your vector or your matrix. Note that here that variables are case sensitive. So if you have a variable named capital A and then common A, these are going to be two different variables altogether. And they will store different values. So you have to be very careful when you're naming your variables that you try to stick to one type of case altogether. You don't want to be mix and matching cases, because then you might accidentally pull the wrong variable when you're required to pull the other instance of the variable. So that's a good programming practice tip. Stick to one case throughout your entire program, be it caps lock or common lock, for lack of a better word. Now, instead of storing vectors and matrices, it's possible for us to actually store scalar values. So we can overwrite our common A variable here, and we can say A is equal to 6 by 7. And you see A here will just give us 42. And we can say capital A here is equal to A by J. And when we type in capital A here, we see that this represents an imaginary value. So imaginary numbers can be represented by J, which is a standard notation in Matlab to say, okay, we want this to be an imaginary value altogether. Similarly, we can say like A is equal to 1 plus 0.5 by J. And we can represent the real part and the imaginary part of a complex number accordingly. Matlab also has specialized functions for certain things. So we can say exp pi by A divided by 42. So what this exp here is, that represents our exponent function, which is e to the power of. And then we can actually type in pi here by itself to actually get the value of pi, which is roughly 22 divided by 7. It can be a little more accurate because of the compiler and so forth. Sorry, because of the interpreter and so forth in Matlab. And then we can just have this entire thing in brackets here being our index for exponent power. We also have special commands in Matlab, so we can type in who. So who will really give us all the variables here that is listed in our workspace. We can type whos to get extended information about these variables. And then if we wish to clear the variables, we can type in clear, or we can type in clear all, and the same thing will happen. If we wish to clear individual variables, so let's say A is equal to 6, B equal to 4, and I wish just only to clear B, I can type in clear B. And you can see here on the workspace that our B variable has been cleared from memory itself. Alright, So are there any particular questions at this point regarding the use of variables and storing numerical notations inside them, and anything regarding specialized functions? Feel free to ask now. Alright, doesn't look like we got any questions. So, okay, let's move on with our material for the time being. So, as we saw a little bit earlier, we were able to do basic matrices. So we could have like A is equal to 3, 2, minus 1, 0, 3, 2, 1, minus 3, 4, which basically gives us an entire row vector. And then we could have B equal to 2, comma, minus 2, sorry, I forgot my brackets, 2, comma, minus 2, comma, 3, semicolon to indicate this is a new row. Yes, you can use commas to separate values and within a row in your matrix, or you can just use spaces, or you can use a combination of the two. Either way is fine. It really comes down to your preference. You can say 1, comma, 1, comma, 0, and then 3, comma, 2, comma, 1. And we see we get our B matrix being a 3 by 3 matrix. Now, let's say if we wish to access a particular element in this matrix, or a particular element in this vector, there are different ways we can go about doing this. So we're going to start with our row vector here. And let's say if we wanted to access the fourth element in our row vector, we can type in A, open normal brackets 4. And you can see here that I'll actually retrieve that value. Let's say if we wanted to get the last value here, we can say A of 9. And you can see that it retrieves 4. And that brings us to an interesting concept here, which is going to be something different between Matlab and your programming languages. So if we wanted to get the first subscript here, or the first value, we'll put a 1. And we've got a 3. Now, this is something to note here. In Matlab, when you start with any indexing or subscripts, you always start at the value of 1. In programming languages, however, you're going to be starting at the value 0 instead. So that's a key difference between Matlab and programming languages. So Matlab, you always start at the index of 1, but in programming languages, you start at an index of 0 instead. That's how it just was created, and I really don't have a better explanation as to why they decided to do this, but Matlab decided to be a little bit different. Similarly, let's say if we wanted to access a... Oh wait, hold on. I have a few questions here. Right, the who function is basically to show the variables that you had here in the workspace. So I can type in who here, and it basically just gives me all the variables that are currently in memory inside Matlab. The who's command basically gives us all the extended information here for for these variables. So it tells us the size of our variables, being if it's a vector or a matrix. So we can see here our A vector here is a 1 by 9, being 1 row by 9 columns. Our answer here, which we were doing a little bit earlier with our subscripts, this is an automatically generated variable. if we didn't specify a variable name. And this stores whatever we have here on the command line if we retrieve some value. So this just basically just stores the scalar value, and you can see here this is a 1 by 1. And we can see that B here, being a 3 by 3 matrix, is also stored here. The bytes here just basically represent how much memory each one of these variables are going to be consuming in your RAM within your computer. So these things don't really consume much memory, and that's because these variables are pretty small. So you don't really need much memory to store these things. So like a 1 by 1 value here, being just 3, just only stores 8 bytes of data. And that's pretty small. But when you start moving on to bigger projects, you won't really get onto it into this course, but probably later on within the degree. You want to see that memory is going to play a very important part. So this whos command is actually going to be somewhat important for you to do what we refer to as memory management. But like I said, in the scope of this course, you won't really be dealing with it. It's just something to note for later use, later on within the degree. Alright. So let's say if you wanted to access elements within your matrix now. Now your matrix is a 2-dimensional array. It's not a 1-dimensional array like your vector. So that means it's going to have an x and y coordinate to access a particular element. So for instance, let's say if we wanted to access this element here, this is going to be on your second row and then your first column. So you're going to have to be b2, 1 to represent the row and column. And we get this value of 1. Similarly, if we wanted to access this value of 0 here, we will put b2, 3, and we get the value of 0 here. Oh, oops, sorry. Nice. And we can keep on doing so forth for whatever we need to access within our matrix. It's also possible for us to add these retrieved values together. So we can say b2, 1 plus b2, 2 plus b2, 3. And this basically just adds all the values here in the second row and all columns as we got it here. So it's possible to combine retrieve functionalities and combination of functions as well into using mathematical operations to achieve different results as of such. Now this brings us to also an interesting concept here for starting our automation in Matlab. So let's say we just wanted to retrieve the entire row here. Now we can put b2, 1, and then we can do b2, 2, and then b2, 3. But that's going to be a little bit tedious. So there's a nice fancy operator that we refer to as the colon operator. And what this does here, it just basically gives us an instance of representing all the values for that particular index that we're retrieving. So for our 2-dimensional matrix here, if I put b2, and then I put the colon operator, this means that, okay, we're going to be on the second row, but we want all the values in the columns associated with the second row. So we're able to get this entire row of values here. Let's say if I wanted this second column here instead. So I could put B, and then I want all rows, column, but then I want all the values in the second column only. So I put 2 here. And we see that we basically extracted that -2, 1, and 2 here as a result. So the colon operator here, the first use, it means that it is able to extract all values for a particular index. Its second use is used for what we refer to as a subscript index as a result. So we can put, in this case, 1:10, and this is what we refer to as a counting subscript index. So 1:10 here means that we start at a value of 1 and we end at a value of 10. And automatically, because we didn't specify how much we want to count by, being what we're going to look at later on being our sampling interval, it just MATLAB automatically assumes, okay, you want to count in increments of 1. So it goes 1, then it adds 1 to that, and it gets 2, and it keeps on doing this repeated operation, 3, 4, 5, 6, all the way up to our end value here of 10. Now let's say we didn't want to count in values of 1. We wanted to specify, okay, we want to count in values of 2 instead. So we could go 1 colon 2 colon 10. And what this tells us is that we start at a value of 1, but instead of adding 1 to that value, we're going to be adding 2 to this value, and we keep on repeating this operation until we reach a value of 10. So we go 1, add 2, 3, add 2, 5, add 2, 7, add 2, 9. And then you realize once we add 2 to this 9 here, we go 11, but that's going to be greater than our end value here, 10. So it basically just stops. And that's the second use of the colon operator here, to give us a counting index for when we're using it. I'm going to see how this is going to be a little bit important later on within the exercise, and how it's going to play a very more importance when you're going to do your post-lab exercise as a result. Now, there's one other thing that I also need to show you regarding this colon operator, and it's that it can be used with functions or specialized variables as a result. So remember this pi variable that we had? It's also possible to use this to count in instances of pi. So let's say we want to go 0 up to 2 by pi. But we want instances such that we want to count in, let's say, probably in pi divided by 4 increments. So we could put our pi divided by 4 increment here, and we know we started at a value of 0 and we ended at 2 pi. And we will get those instances here. So this will be 0, pi on 4, 2 pi on 4, 3 pi on 4, 4 pi on 4, 5 pi on 4, and so forth as we keep on going. So this gives us a nice indication of how we can use this counting subscript or this counting index here to automatically generate values in a repeated pattern. And this also is going to be very important later on when we also get to plotting for us to start automatically generating our values and so forth. I think there was one other thing I wanted to show you guys with the B matrix, and that would be that, let's say if we didn't want to extract out all the values for a particular column or a particular row, and let's say, okay, in this instance, we just only want the first 2 rows. So we can say B, open brackets, 1 colon 2, comma, and then we want all the values in the columns. So this is also a nice instance of how we can actually do specific extractions for particular rows within a matrix. So we say, okay, we want the first 2 rows, being we go in row 1 to row 2, and then all the column values as required. Let's say if we didn't want all of this, and we just wanted 2 minus 2 here, and 1, 1 here, being just these 4 values, we can say B, 1 colon 2, comma, and then we just want all the values in the first column and the first row associated with this, 1 colon 2, and we do this extraction here as a result. So that's perfectly fine regarding using the colon operator here for extractions within our matrix and so forth as well. Alright, so before I go on to script functions, any other questions that need to be asked, feel free to ask now. No, this session actually is not going to be a recap of the Matlab on-ramp, because you're going to see a little bit later on, we're going to do some specialized stuff. There's going to be a few other things inside it that's going to be building on it. So you may see one or two things that may have some overlap with the on-ramp in the start here. But once you get those out of the way, you're going to see stuff that's going to be a little bit different from the on-ramp course. And it's going to actually prep you guys for your post-lab exercise as a result as well. I'm just discussing these key points here just as a refresher, in case of anybody who is still in progress for the on-ramp course, or in the rare instances, people who may not have started as yet. So just bear with me a little bit. Alright, okay, so let's go on to scripts, not script functions, and actually how they can be used in Matlab itself. So far we've been typing in all our commands here on the command line, and we realize that it's not really stored anywhere. Yeah, there's a bit of a delay in the YouTube chat. I think it's probably a few seconds. So it's okay if I see the questions. Once I see a little bit late, once I do see them, I will address them. Yes, the session will be available to rewatch again once the session is finished. It's automatically recorded, so it's normally up in like about 3-4 minutes in case you need to review them. Alright, so let's get on to scripts. And so far you've been seeing that we've just been typing in commands here on the command window, and we haven't really have a way to save these commands to use later. And that brings us to what we refer to here as a new script on the top left-hand corner of your Matlab. So if we click on this, we see that we get a script editor. And we actually can store all our commands that we've been using so far inside of this editor, and then we can save it for later use. So, for instance, let's say, just for simplicity's sake, we're going to just store the a equals 6, b equals to 3 to 1, 1 to 1, 1 to 3. And we may want to run a clear command to clear anything that may have been there. So we can save here, and let's just call this example 1. So once we save this here and we have example run 1 in our current folder that we're working in, we can just hit the run button here. And this actually will run all these commands here that we've saved in example 1. So we can see A and B here was created successfully in our window. And we can add other commands inside here as well. So I'm going to put a whos command. And then we can run this again, and we can see that we get our output here accordingly as of such. So scripts are a very nice way of saving our work for later review that we may have just been testing out in the command window, but we do want to have some reference to it later on. Scripts also give us an introduction to what we refer to as using our custom functions in Matlab. So, for instance, let's say we wanted to create a particular function. So I'm going to close off the script here, and let's make a new one. And let's say function distance equals to dis2 ax ay bx by. And we're going to make sure that this function calculates the distance between two known coordinates. So we say distance is equal to the square root of bx minus ax to the power of 2 plus by minus ay power of 2. And let's save this as dis2. So what this function basically does here is that it gives us an output name here for what we need to return, being the result of the function. And we give our function the name here being dis2. And inside these brackets here, these are going to be the input variables to our function. So think about it similarly like an f of x function or f of y function that we have seen in maths. Now it's going to be f of x1, x2, x3, x4. Or in this case, it's going to be ax, ay, bx, by. And these input variables here, are, as we're going to see when we start using our function here in our command window, it's going to be what we need to pass into this function here for it to operate. Now I can hit run here, and you're going to see, we're going to see not enough input arguments. And that's because this here being a function, we need to specify 4 input variables here separated by commas for the function to work. So in order to use this, we're going to have to put this 2 here in our command window, and we can put 2 coordinates. So let's say 1, 1 being our first A coordinate with x and y. And then we can put, let's say, just for simplicity's sake, 5, 5 being our B coordinate with x and y. And when we hit enter here, we see that it actually calculates the distance for us between these 2 coordinates. And it's given by our formula here that we wrote. Now, this could be a little bit tedious to keep on putting in multiple values. So, like, let's say we want to do this 2, 1, 2, 3, 4. And we need to keep on repeating this. It's a little bit tedious. It's also not very user-friendly. So, we're going to have to make something we refer to as an interface to call this function in the background. And we can also use an interface as a result to access this function by also creating another script file. So let's go ahead and do that, and let's go new here. And in this script file, let's call this our interface. And we're going to have to do a little bit of outputs here. So we're going to call it display command and say calculate distance between points. And then say ax equals to input. The input command here allows us to input a value from the command window. So enter x value of point A. And instead of me having to type this, we're just going to copy this line 3 more times. And just change the variables. So let's say x, a, y. Enter y value here, then x, point B, and then by for point B as well. And then let's say here we're going to say result is equal to our dis2 function that we just created. And we're going to pass ax, ay, bx, and by that we had here in our previous instances of our lines that we just now typed. And let's say we just want to do something a little bit more fancy and we wanted to output what the result is. Distance between points A and B is %f/n result. And let's save this as test this2. All right. So before I actually run this interface function here that we just now created, I'm going to explain 2 things that you may not have any sort of explanation to, that may have been explained inside the on-ramp. It may have, it may not have, but I'm just going to repeat the explanation in case that it was explained. So this %f here is a placeholder for any variable that we wish to put in our output function, being fprintf. So fprintf here is basically just an output function that allows us to print some text onto the screen. And we can also use placeholders for any particular variables that we need to put as well. So that's why we have this %f here. The /n next to the % just basically means to have the output on a new line. So that's what those two particular variables mean here in the context of our test this2 function. So this test this2 function here is going to be the interface for our this2 function that we created here previously. And we can run this instead of having to call it on the command line here that we saw here for this2. And it provides a nice clean interface for us to do our calculations. And under the hood here, it actually calls the this2 function by passing the 4 values that we have here that we need to input, and then calculate it and return the output value in a nice fashion or a nice format. So let's run our test this2 function here. And you can see here, it's going to say calculate the distance between the 2 points. We need to enter the x value for point A, so I'm just going to repeat myself. 1, and then the y value, 1, for point B, 5, and 5. I'm going to see here the distance between points at B, A and B here is, and we get the value as required. And let's say if I just wanted to put print f here just to add a little bit extra to show you that the new line does work, and a program. And let's run this again. 1155. See, it's going to be in the program here. And you can see that that /n here gave us the new value as required. So I'm just going to remove this here because that wasn't in your script, so anybody who's following can actually just see how it actually works as accordingly. So any particular questions on using the function inside your script files and then using the interface to call that function in your script file, feel free to ask now. Alright, so answering in Q here. So the %f here is just a placeholder for us to actually put a variable in our output statement. So all %f here being a placeholder, it knows afterwards inside this fprintf command that anywhere it sees %f, it needs to replace this with the result variable as accordingly. The /n here, it just basically means we're going to start this on a particular new line. So let's say for arguments, let's remove that /f. And let's run this to see what happens. 1155. And you see here that it will say the distance between points A and B is whatever. But then we have this floating command here being like, okay, we're still on the current line here. So we're not on a new line as accordingly. So if we wanted to get out of this line here, being that our command window is still at this particular line and it's just going to be started here, we can just hit Control-C on our keyboard to go back to a new line accordingly. So that's the importance of having that /n variable here. Oops, that's wrong. This will be inside here. Nice. So the input function is input, and the output function is fprintf. There's also another output function that we can call named disp, which we saw earlier, being this one here. And we can put end of program here as well. And we can run this accordingly, 1155. And you can see disp here automatically gives us this new line being the /n any way that it does end as a result. The function and interface scripts typically should be two different files. There is a way to combine the two, but it tends to get a little bit confusing when you start using more and more functions. So it is always highly recommended to separate these into different files. Because when you start trying to put all this into one file, and especially when you have multiple functions and so forth inside there, it's going to get a lot confusing to manage everything. So yes, it is possible, but it is not recommended to put everything in one file. Always try to separate your functions and your interfaces into separate files. And this also is another programming tip for Matlab and programming languages. Alright, any further questions? Alright, doesn't seem like we've got any further questions. Okay, let's move on. So, one thing to note here is that in Matlab, you can't have variables starting with particular characters. So, you can't have a variable starting with a space or a special character, and you try your utmost best to avoid the use of numbers in your variables. So you don't really want like A1 or A2 or anything of the sort. You try your best to avoid that. You try to make sure that your variables are word named instead of some sort of special character name or so forth. Like let's say if I put exclamation A here, you already see that just because the text here changes into a different color, the special character already has some sort of functionality inside Matlab. And plenty of the special characters on the keyboard do have some sort of functionality in Matlab itself. So you try not to use these characters. So like the exclamation, the at probably has some other functionality, the hash symbol, the money symbol, %. You see, once you start changing different colors, they have some sort of function. So try your best not to have any special characters for your variable names, and try your best not to have any spaces in your variable names as well, because the spaces typically aren't picked up by Matlab to be, okay, this is going to be one continuous variable name. It thinks it's going to be two separate things altogether, and that runs into problems. So always try to make sure your variables are some sort of word name variables, without the use of special characters and without the use of numbers. Alright, so the next thing that we're moving on here to is plotting. And plotting is going to give us an instance here of what we can look for in particular when we need to display our data in some graphical format. So because we're using script files, so I'm just going to create a new script file here. And let's say we wanted to plot our sine graph. So let's say x is equal to 0, colon pi by 100, colon 2 by pi, and y is equal to sine of x. Now for the instance here, I'm just going to put plot y, and I want you guys to see what's going to happen. So let's call this plot test, and let's run this. So what plot says here is that if we just put a single variable in our plot command, all it does is just plot this accordingly using only the values of y, but there's no reference value of x here for it to go to. So if things okay, it's going to start at 0 here and go forward towards some instance. So for every instance of y here, I'm saying this wrong, it's going to start at the value of 1 because MATLAB always starts at 1. Sorry about that. So for every instance of y here, it's going to be like, okay, for the first value of y, that's going to be the first value here on the x-axis. For the second value of y, it's going to be the second value here on the x-axis, and so forth as we keep on going. If we put plot x divided by, x comma y, run this. In this case now, it does have an x vector here to make a reference to the y values. So this gives us our x and y coordinates as a result. And you can see if I click here, you'll see there's a corresponding x value and a corresponding y value represented in our coordinate geometry. Just to highlight this, if I go back to plot y and I run this, and if I click anywhere here on the graph, you'll see it's going to be for the 20 value in the y vector, this is going to be the corresponding value. Similarly, for the 35th value, that's the corresponding value. For the 98th value and so forth, that's what's going to happen. So if you don't have an x vector to map with your y vector, it's just going to use the placeholders for where the location of the value is in the y vector as a result for that particular plot. Now let's say we also want to make sure that we label our axes here. So we can put x label, x is equal to 0 to 2 slash pi. Y label, line of x. And then title, dot of the sine function. We can also do some other specifications, be like we can say what our font size needs to be, font colors and so forth, but you don't really need to do all of that unless you want to get really fancy. And we can run this. And we can see here that as a result, we get our nice sine function here with our axes label and the title of our graph label as a result. And we see that because we specified the font size here in our code, we see that the font size here for the title is different from the font size here for x and y axes labels. So the reason why I went to this plot code here for this particular instance and for this particular explanation is to bring up a topic that we normally refer to as sampling. Now, sampling is going to be a very important topic anytime you deal with anything in the digital domain, because we are so accustomed to using these things and plotting it on paper and watching it as a mathematical function in continuous time. So that means that once you know what the function is, we can put any value for its input, and we'll always get a corresponding value for its output. However, in your digital domain, or for any digital signals that you're going to be using, these signals are not plotted in continuous time. They are plotted in what we refer to as discretized time or discrete time. That means unless you specify these values for the input, you will only get the corresponding values. Sorry, you'll only get the corresponding output values for those particular input values. Let's see how this effect actually looks if we don't sample properly. So this content index here that we have been using all the time with our colon operators, we want to see why is this content index here important when we're talking about sampling. So instead of going in increments of pi divided by 100, let's go increments of pi divided by 5. And if we plot our graph, so let's run this, we can see here that what happened? Why is it that it's no longer that nice smooth sine graph? Why does it look like it's a bunch of straight lines just connected to one another? And this is because, like I said, in the digital domain, your signals are in discretized time. They're not in continuous time. If it was in continuous time, you get that nice smooth sine curve. But because of the discretized time, it's going to end up as a result looking like this. So it's just going to be straight lines connecting from point to point. And this is what we also refer to as a straight line approximation, which is very common for discretized time graphs. So this interval here, or this constant index that we use here to specify our x vector, in sampling we refer to this as the sampling interval. I'm going to see why this sampling interval here is going to be important for obtaining nice smooth graphs. Now, you may be saying, okay, yes, it's a straight line approximation, but yeah, we can just increase this and we'll just get a nice smooth curve. But it's also important to note why we result in a nice smooth curve. So instead of putting plot here, let's put stem. And if we run this, what the stem does here, it actually shows you what each one of these values here represent in our discretized time signal. So there's no in-between values. These are the only values that exist for our y signal here being sine of x. And the reason for this being is that we only have x of 0 being y of 0. When x goes to pi divided by 5 here, we have y as a result, but there's no in-between value here for anything between 0 and pi on 5. These are literally the only two values that exist for our sine graph as a result. And this is because of the discretized nature of the signal when you're dealing with digital signals in particular. So the more data points that you do have, you reduce the straight line approximation effect and you get a nice smooth curve. But the less data points you have, your straight line approximation effect is greater, and then you see that thing looking like it's just a bunch of straight lines connecting from point to point, and you don't know what the shape of the signal actually looks like. So the only way to resolve this error is to make sure that when you're using some signal in continuous time in your mathematical notation, you want to make sure that your sampling interval is going to be small enough such that you reduce the straight line approximation effect when you move into the digital domain or discretized time. So to give you an idea of what this looks like, let's go from pi divided by 5, let's go pi divided by 6 on this. And you see that, okay, we can start getting more points. Let's go pi divided by 10. We start getting more points, and we can actually see that the curve actually starts filling out nicely if we start doing straight line connections. And as we keep on going up, so let's say pi divided by 30, we have more and more points to actually give us this curve, reducing the straight line approximation effect. So eventually when we go back to pi divided by 100, because we have so many points, that straight line approximation effect is so little that it just looks like if we have the curve as a result. All the plot command does, it just joins these points, giving us a nice smooth curve here. And you can't really notice that unless you use the stem command to see, okay, what the signal actually does look like. You just automatically think it's just going to be a nice smooth curve. But because you saw it in the stem command, that's not the case. So always remember this when you're dealing with any signal in the digital domain. It is represented in discrete time, not continuous time. So you need to make sure that your sampling interval here needs to be very small in order to get the nature of what your signal actually is supposed to look like. If it is not small, they want to get that straight line approximation effect. Now, there's also such a thing that having a too small sampling interval. Because remember, as this goes down, that means this x value here is going to continue with more and more values as a result. So let's just highlight this a little bit. Let's go back to when we had it divided by 10. And if we watch x here in our workspace, we see x here is a 1 by 21, meaning that it contains 21 values. But when we go up here, and when it was pi divided by 100, let's run this, we now see that x here is a 1 by 201 double. And that means it now has 201 values. Let's just go up by 1, let's say if it's 1,000, you're not going to see here that it's 1 by 2001. So the more values that you have here, and you can see it if we type whos, you're going to consume more and more data. So there is such a thing as having too small of a sampling interval, and there is also such a thing as having too large of a sampling interval. So once you have something in between that balances your memory requirements, and you still get the correct result as required, you're perfectly fine. You don't need to get more points. You don't need to worry about having less points. Once you know what that range is for you to get that nice smooth curve, you're able to just stick with that, and you don't need to consume more memory, and you don't need to worry about do I need more points for my graph as a result. Now, this sampling concept that I just now discussed here is going to be very important for when you're going to be doing ELAB 2. And that in particular is going to be when you start doing ELAB 2 and you're going to have to do a particular graph or a few graphs, you need to make sure that when you take your points from the continuous time graph to represent it in discretized time here in Matlab, that you took enough points and you sample that continuous time graph properly in order to get your nice smooth curve graph. If you didn't sample properly, it's going to end up like that straight line effect. So keep that in mind in particular when you're going to be doing ELAB 2. You need to make sure that once you have your continuous time graphs, you do sample them properly and get enough sample points to get a nice smooth representation. If you don't sample properly, you're going to be in a lot of problems, and I think as a result from this semester, you're going to lose marks entirely for not having that nice smooth graph. So don't say I didn't warn you. I warned you guys up front. Watch out for that in particular when you're going to be dealing with ELAB 2. Alright, are there any particular questions regarding the topic of sampling here? Feel free to ask now. Okay, it doesn't look like we had any questions on sampling. Alright, so let's move on. Now, similarly with your graphs here, it's also possible for you to have multiple data sets in one graph. So we had y equals to sine x here, and then y2 equals to sine of x minus 0.25, and y3 here is equal to sine of x minus 0.5. And we can have plot xy here, and we can do multiple plots, xy2, xy3. Let's run this. And we can see here that we can get our 3 plots here accordingly as a result. Yes. So there is a way to predict how many samples you'll need in particular. So let's say if you're having some sort of sine curve here for this entire thing, and this is a nice instance of knowing about this. We have such that we need to go in intervals of pi divided by 100. And we're going up to 2 pi as a result, meaning that we end up at 201, right? But let's say instead of going pi by 100, we go pi divided by 20. We see that we still get a nice smooth graph as a result. And that just means we end up with just 41 values. Similarly, when we had pi divided by 10 here, we see that, yes, we do have some straight line approximations going on here, but it's not so horrible. And we can see here that it was just only 21 values that we required. So a nice instance is that if you're doing something that has a period, you try to take at least 20 values. So that's a nice okay number to start with. You try to make sure that you have at least 20 sample points. Anything more is welcomed, because that just means it's going to go up in accuracy. But at the very least, it needs to be 20 sample points. Alright, continuing on. So we just saw here that how we can go about plotting multiple data sets on the same graph. We just use the same plot command, and we say, okay, this is going to be the first data set, this is going to be the second data set, and this is going to be our third data set. And we can keep on going doing that. It's also possible for us to specify line styles and color markers for our plots, if we wish to. So I can put a percent here, and what this percent symbol means is that we're going to comment this line. Now, commenting that line means that line won't run in code, but it still does exist in our file in case we need to get back to it later on. So I can put plot x, y, c. It should run. Alright, and we can see here that C here gives us a nice cyan color for our graph. We can also put comma dash dash, and put this in quotes. Change our line style. Oh, whoops, that one didn't work. See why that didn't work. I probably have to use a line style marker, or whoops, or I may have to try the plus here. That works as well. No, that won't work. Alright, give me one instance. Plus. Right, so I'm gonna have to use line style. Right, and there we go. Plus. Nice. Oh, right. Okay, so plus is not a current line style. Double dash. Right, there we go. So we got our dashes here. And then we can also put comma here, and we can put marker, and then we can choose what marker we want. And run that. And we can see here that we get our nice plus signs as of such. Okay, so let me just get rid of this cyan. I know it's a bit bright. Let's run this. And we can see here that we can get this. Now, how did I get that? So let's go back to our standard plot xy command here. So after I have plot xy here, I can just put comma and open a single quote. And I can put like line style, just type in an L, line width, line join. I can type in C here and you will see like color, and we get all these additional functionalities as a result. So like if I put color, the next thing that comes up here would be that once I put the quotes, I can put X here, or I can put anything else as a result. So using these additional functionalities in the plot command gives us a ways to customize our plots. So let me just, I'll leave this here. Just comment this out using our percent symbol, and uncomment that by removing the percent symbol here earlier. And if I run this, you see we go back to our triple graphs that we had from before, and we don't need to worry about anything with color here or so forth as a result. This line here just won't run in our entire script. It still exists, but because we commented it, it will not run. Alright, so that basically brings us to the end of discussing plots. We only have 2 more things to discuss in today's session. So the other thing that we need to discuss here, in the second to last thing, is what we refer to as Boolean. Now, Boolean values basically are just going to be true and false. So like, for instance, if I type in that's clear or variables here, I type in a is equal to true. See, a here will just get a value of 1. If I typed in a equals to not true, a here will get a value of 0 because the opposite of true here being not true is going to be false. So a value of 1 evaluates as true, a value of 0 evaluates as false. Boolean logic plays an important part when we go on to what we refer to as conditional statements. Because conditional statements mean that basically if this is true, we need to do these particular statements. Elsewise, being that if it was false, we do these particular statements instead. So let's just run this in the script to illustrate what it looks like. Let's say b is equal to false. Let's say if b, display false. Else, display true. Now we put an end here to indicate that's the end of our thing, of our statements. So it's conditional. And if we run this, we see that we return a value of true. Now why did we return a value of true here? So what happens here is that b here was false. And we have if b. So what does if b here means that we need to evaluate if b here is equal to true. So if b here was equal to true, we need to actually display false here. But because b is actually false, we display true here as a result. We can also use this in a different way instead of using the Boolean logic. So let's just comment this out. And we can use this with any other variables as required. So that's a equals to 2, b equals to 3. And let's say if a compares to b, so this double equal sign here means compares to. A single equal means it's assigned. Don't mix up the two. It's easy to mix up the two. Display true. Else, display false. And because the two values here are not equal to one another, or do not compare to one another, once we run our code here, we see that we get a value of false being displayed. So the condition here in our if statement checks to see if this actually is true. So if it was true, meaning that if A and B had the same value, it will only execute the statement here. Because it's not true, meaning that it's false, it ignores this statement here because it knows not to execute it, and then it executes this part here instead to display false. So conditional statements are a nice way of doing particular branches in your code for particular types of execution. So it allows us to do what we refer to as decision making in our code. And for particular decisions, you only want this section of code to run. You don't want other sections to run as a result. Similarly, we can chain if-else statements together. So we just only had two branches here. We can go more than two branches. Let's comment this and put x equals to 10 here. And we say if x is more than 10, display x is more than 10. Else if x is less than 10, display x is less than 10. Else display x is equal to 10. So if we want to use more than two branches for our decision making here, we use the else if statement, and we also specify a different condition that we need to be checking for as a result. So if we run this, because x here is equal to 10, we're not supposed to get this line running, we're not supposed to get this line running, we're supposed to just only get x is equal to 10. And once we run that, we see x is equal to 10. If we switch this to 10.5, we're supposed to only see that x is more than 10. So let's run this, x is more than 10, and if we put this down to 9 and run this, we get x is less than 10. So depending on the value of x here, we can go about checking to see if it's going to be more than, less than, or equal to, and just only run the particular statements for those particular conditions. So compare to basically does what we refer to as a comparison. So I'll give you an instance why that compares is important, right? So let's go back to this code here. Oops, I didn't need to do that. Comment this, and then uncomment this. If I put A equal B here, and I run this, you want to see unsupported use of the equal operator. And then to compare values for equality, use double equal. So a single equal means that you assign a value to a variable. A double equal means that it compares two values to see if they are equal to one another or if they are not equal to one another. If we have to use different grammatical terms here, a compare being here, being the double equal being the compare operator, means to see if these two variables contain the same value. If they do contain the same value and that results in a true, then you execute your statement as a result. But if they do not contain the same value, you execute the other statement given by the else branch here. So that's why you need to have a difference between assign and compare to. Because assign means store this value in memory. Compare to means, okay, check and see if these two values are similar or they are the same value. Right. Out. Yeah, one is assigning, the other one is checking. Now, it is also possible to nest if statements within other if statements. So we could put x equals 25 if x is more than 10. And then we can also put if x is less than 20, y is equal to 1. And then we can put else y is equal to 2. And we end that here, and we need also to end this here as well. So in nesting multiple if statements, we need to make sure that for every if statement, there's a corresponding end or a corresponding else as a result. So for this one that's nested here, we need to make sure that if starts here and then there's an end. And then for this if statement here, we also need to make sure that there's an end statement here as a result. Let's say if I did not have this end statement, and I try to run this, the interpreter here is going to throw an error and be like, okay, an end is missing. So there's no matching end for this particular if. So you need to make sure that for every if that you have, there is a corresponding n as a result. So in nesting these if statements here, the first check is going to be if x is more than 10, but then inside here we need to also check, okay, is x going to be less than 20? X here has a value of 25. So that means it's not in between 10 and 20. So we're not going to have y equal 1 here, we're supposed to get y equals to 2. So if we run this state, we see y here has a value of 2 as a result. However, if it was within range, so let's say 19, we see y here gets a value of 1 once we run our script. Now, what happens if we actually put it equal to one of these values here, being 10 or 20? Do you think you'll get y equal to 1? Or do you think you'll get y equal to 2? So I'm going to poll you guys here. And let's see how the responses look. And then we're going to actually verify it. So for this particular instance, when x is equal to 20, which one of these outputs do you think we are going to get? Give it a few, let's give it like 1 more minute to see how the votes are coming in here, to see what people think. Alright, 15 more seconds for voting. close it in 3, 2, 1. Alright, let's end our poll here, and let's see what the results look like. Alright, so the majority of people voted for y equals 2. So let's run our code and see what it does look like. And yes, we did get y equal to 2. Now for the people who voted y equal 1, don't feel bad. This is something that you do have to make sure about when you're verifying your code. You see, when you have x more than 10 and x less than 20 here, these do not include the actual value of 10 and 20 as a result. It just means that for anything that is going to be more than 10 and less than 20, being exclusive of these values, that's only the things that you're going to be checking. So it could be 10.00001 all the way up to some decimal value once we have that 1 there. Once it's in between 10 and 20, you will get a value of 1 here. But if it's actual 10 and 20, these being limits here, these aren't included in the check. So that's why you're going to get y equal 2. Now, if you did want 10 and 20 to be included in the check here, for you to get y equal 1, we can put x is more than equal to and less than equal to in order to get this being inclusive of 10 and 20 in our range check. And once we run this, we will see here that y here, that's a value of 1 instead. So this is one thing that you need to be very careful about. When you do operate with ranges, you need to make sure that you, if you're using more than and less than by themselves, that the values that you specify there are not going to be included in the range. These are just going to be the limits. Anything in between there is acceptable, but the limits won't be included for your checks in this range. If you do wish to include the limits as part of your range, you're going to have to use more than equal to and less than equal to as a result. So that's another programming tip that you need to pay attention to. If you use a more than and less than, your limits aren't included in the range check. But if you do wish to include limits, you need to use more than equal to and less than equal to include those limits within the range check. All right. So the other thing, and this is going to be the last topic that we're going to be discussing for today, is loops. And loops is like a really nice way of doing automation for particular instructions that we wish to keep on repeating, but we don't have to write it out like 10 or 20 times and so forth. So the first instance of a loop here is basically what we just saw for our counting index with our colon operator. So you can have for x equals to 1 colon 1 colon 10, x here, and end. And let's just call this loops. Let me just clear my workspace. Now if I run this, and close this off for the time being, you'll see here that we have x1, x equals 2, x equals 3, 4, 5, 6, going all the way up. And this is just basically repeats this value as a result. Now, one thing to note here that's going to be a little bit different from actually just having the x vector. X here is a scalar value. So, because we use x here in a loop construct, back up. There we go. Because I use x here in a loop construct, and I didn't use it as a vector construct by itself, this means that when we go in scalar values of x instead of having the entire vector of all the values of x. So I will start at 1, display this 1, and then for the next increment of the loop, I will add 1 here to that value and give us a value of 2, and keep on repeating as it goes counting from 1 to 10 in increments of 1. It is also possible for us to nest if statements and multiple for loops inside here. So I'm just going to give you one instance where we have for y equals to 11, 1, 13. We're just going to output y here. And if we run this, and let's just close this off, we can see what it looks like here. Be that it'll go x equals 1, 2, 3, 4, 5, 6. Oh, oops, sorry. So we can have x here is equal to 1, and then for when x is equal to 1, we have 11, 12, 13 being outputted there for y. And then we go to the next increment of x equals to 2, 11, 12, 13, x equals to 3, 11, 12, 13, and so forth. And this is basically how the nature of the loop operates. The outermost loop here will be responsible for controlling how many times the innermost loop here is going to run. So for every instance of a value of x, the value of y here needs to run until it's completed for that particular instance. So that's why you get x going 1, and then y is equal to 11, 12, 13, x equals to 2, y is 11, 12, 13, and so forth. So let me see if I can just bring up something here to give you guys an idea of what this looks like, just to illustrate it. So we know x here is going from 1, 2, 3, all the way up to 10. And we have y here is going 11, 12, 13. And because of the nature of a loop here, being that this y loop is inside the x loop here, that means that we need to make sure that for all the instances y counts, it needs to be for every instance of x. So what this looks like is that when x is equal to 1, y needs to go 11, 12, 13. And then x equals to 2, y repeats itself, 11, 12, 13, and then x equals to 3, and y repeats itself, 11, 12, 13, all the way down to x equals to 10, y equals 11, 12, 13, and then it will just basically stop. So that's why you notice that in particular in our code here, when you had x equals 10 here, being the last instance, and then y goes 11, 12, and 13 as a result. So when you're embedding loops, remember the outermost loop is what's going to be controlling the entire instructions inside. And how many instances of those instructions being repeated is controlled by that outermost loop. All right. So any particular questions on conditional statements or loops, feel free to ask them now. Also seen a question I missed. I do apologize for that. There's no key difference between fprintf and display. There's either one that you want to use. It's just different formats on using fprintf or display. Either one is fine to use. You can mix and match the two. If you have a preference for one, that's fine as well. So fprintf, you will have to use the %f. Display, on the other hand, you don't have to absolutely use that %f. So it's either one that you want to use. There's no key difference between their functionality, just how they're implemented is just going to be the difference. So the reason why it didn't go here in the loop x equals 1, y equals 11, x equals 2, y equals 12, because this outermost loop here, you need to make sure that all the instructions here completes before it can go on to the next particular value. So that, like, when we start here at x equals 1, all these instructions need to be completed here until we can go to the next value of x equals 2. So x equals 1, these instructions say need to complete first. So this goes 11, 12, 13, and then once that completes, it then can go to the next value in x here being 2 and repeats as so forth. So yeah, the nature of the display function is that you can just put the variables in and it will just show up. So let's just do a quick test there. Comment this out here for the time being. Say a is equal to 2, 3, and I can probably put display test a b. That should work. Nope, too many input arguments. Well, I figured as much. I can also put like display a, and that should be fine. Test. Yep, figured as much. So I know for sure, in particular, that there's a way to actually have input arguments being, sorry, for you to display variables using the display command. But I will check that back in a little bit, and I will post the answer for that on the forum on how to use it. The yellow arrows on the side are basically just placeholders to indicate where the interpreter might think it actually does have an error in your code. In some instances, you may not even get any. But it does just basically gives you like an error, or basically some cases a warning where things may go out of control in your code itself. Alright, any more questions? Yes, the exercise B is your post-lab exercise that is worth marks for the course. The practice exercise here for 1A at the end of this 1A script in particular, that's actually you to actually practice, and if you do encounter any problems, make sure that you do post your questions on the Matlab support forum. If I can address them immediately, I will address them to you directly on the forum. If not, I will be going one-on-one with you guys in the carded demonstration session. And I'll give you guys individual feedback once you start showing me your attempts and where you start getting particular problems. Those particular problems, like I said, because we're going to be doing that one-on-one, we'll be going into Blackboard Collaborate. Now, the reason why I'm here on YouTube is because if I'm dealing with 100 and something of you guys at once, Blackboard Collaborate, yes, it's a great platform, but it tends to fail a little bit once the class size goes really huge. And if I'm doing one-on-one sessions, I actually can hear you guys and see your screens as of such, so I'll be moving back into Blackboard Collaborate only for those demonstration sessions. Like I said, the only time I'm going to be doing that is you need to post any particular problems that you are encountering on the support forum, so I know who it is that I'm going to be dealing with on that particular session. If I can't address them on the forums, then we're moving on into those one-on-one particular sessions to directly address problems you are encountering and any sort of feedback that you may require. But if your Matlab has expired now, if you do have a my.ue.edu address, because you're supposed to have one of those at this point, you actually can log in on Matlab using that particular address. And you can actually make a free account on Matlab's website using that particular email as well. And it will automatically give you access to the university license, and you can get a full copy of Matlab legally throughout that channel. Because the university right now is paying for a huge Matlab license bundle. All right. So just recapping, basically, I know I told you guys, bear with me a little bit, some of this stuff that we talked about here was covered in the Matlab on-ramp course, but there were some tidbits that I did talk about that is going to be important for you guys in later assignments and things to look out for with respect to scripting and programming languages and the difference between continuous signals and discretized signals. So those particular points are very important regarding those things in particular. Now, at the end of this session, at the end of the 1A script, there's a practice exercise. I want you guys to actually attempt that practice exercise. And if you do encounter any particular problems, feel free to post them on the forum and let me know. If I can address them immediately, I will address them. If not, then I'll be having a one-on-one session with you guys at the carded demonstration time. I believe this will be next week, Monday. If there aren't any problems at that point in time, we will not have those particular sessions for those one-on-one. But if you do need the one-on-one feedback, please make sure that you do post the problem on the forum. And like I said, if I can't address it immediately, I will make sure card that time for that one-on-one feedback. Those particular sessions, because it's one-on-one, it's going to be Blackboard Collaborate, so I'm going to have to see your screen in order to see what particular problem you're having, and I can give you particular feedback as required. If there are any further questions regarding what we did today, feel free to leave them down in the comments below, post it on the support forum. You can directly email me. Once I get in contact with you, or you get in contact with me, I can address your problems as required. So, until our next session, take care, be safe, and I will see you guys soon. Later.